Welcome to our exploration of data transfer in computer systems. In this video, we'll break down how data moves between registers, buses, and memory. Understanding these pathways is crucial for grasping how computers process and store information. We'll start by introducing the key components involved, then dive into the mechanisms that enable seamless data movement. Whether you're a student, a tech enthusiast, or just curious about how computers work, this journey will clarify the invisible processes happening inside your device every second. Let's begin by defining what registers, buses, and memory are and why their interaction is so essential. Registers are small, high-speed storage locations found directly within the CPU. They temporarily hold data and instructions that the processor is currently working with. Because of their proximity to the CPU's core, registers enable rapid access and manipulation of information, making them essential for efficient processing. Think of registers as the CPU's immediate workspace, where the most critical operations happen. Their size is limited, but their speed is unmatched compared to other storage types. Next, let's see how data gets from these registers to other parts of the system. The bus acts as a communication highway within a computer, connecting various components like the CPU, memory, and input-output devices. It consists of a set of parallel wires or traces that carry data, addresses, and control signals. Without the bus, data would have no way to travel between registers and memory. There are different types of buses, such as data buses, address buses, and control buses, each serving a specific role in managing information flow. Now let's look at how memory fits into this system. Memory, often referred to as RAM, is where data and instructions are stored for quick access by the CPU. Unlike registers, memory can hold much larger amounts of information, but it is slower. When the CPU needs data not already in a register, it retrieves it from memory via the bus. This process is fundamental to running programs and managing tasks efficiently. Next, we'll see how these components interact during a typical data transfer operation. Data transfer is the process of moving information between registers, memory, and other components using the bus. This movement is orchestrated by control signals that determine when and where data should go. Efficient data transfer is vital for system performance, as delays can slow down the entire computer. Let's break down the steps involved in a typical data transfer from memory to a register. The first step in transferring data from memory to a register is placing the memory address on the address bus. The CPU determines which memory location it needs and sends this address out. The address bus carries this information to the memory module, ensuring the correct data is accessed. This precise targeting is essential for accurate data retrieval. Next, the system prepares to read the data. Once the address is in place, the CPU sends a control signal, typically a read command, to the memory. This signal travels via the control bus, instructing the memory to prepare the requested data for transfer. Control signals are like traffic lights, coordinating when data can move and preventing conflicts on the bus. With the command given, the memory is ready to send the data out. With the address and control signals in place, the memory places the requested data onto the data bus. The data bus is a set of wires that physically carries the bits from memory to the CPU. This transfer happens rapidly, but only when the bus is free and the control signals allow it. The CPU then captures the data and stores it in the appropriate register for immediate use. Data transfer isn't just one way. Sometimes the CPU needs to write data from a register back into memory. This process is similar but uses a write control signal. The CPU places the memory address and data on their respective buses, then signals the memory to store the incoming data. This ensures that processed information can be saved for later use. There are several types of data transfers in computer systems. These include memory to register, register to memory, register to register, and memory to memory transfers. Each type serves a specific purpose, depending on the operation being performed. For example, register-to-register transfers are extremely fast and used for immediate calculations, while memory-to-memory transfers are less common and usually handled by special instructions. Register-to-register transfers occur entirely within the CPU. Data moves from one register to another without involving the bus or memory. This is the fastest type of transfer, as it doesn't require external communication. Such transfers are common during arithmetic and logic operations, where intermediate results are quickly shuffled between registers for further processing. When the CPU needs to store results for later use, it performs a register-to-memory transfer. The data in a register is sent out to a specified memory location via the bus. This process involves placing the address and data on their respective buses and signaling the memory to write the data. It's essential for saving computation results and maintaining program state. A memory-to-register transfer is used when the CPU needs to fetch data from memory for processing. The CPU specifies the memory address, and the data is transferred into a register via the bus. This operation is fundamental to program execution, as instructions and data must be loaded into registers before the CPU can act on them. Memory-to-memory transfers are less common and typically require special instructions or hardware support. In this operation, data moves directly from one memory location to another, often using the CPU as an intermediary. This can be useful for copying large blocks of data, such as during file operations or system initialization. Bus arbitration is the process of managing access to the bus when multiple components need to use it simultaneously. The system uses control logic to decide which device gets priority, preventing data collisions and ensuring smooth operation. Arbitration is crucial in complex systems with multiple CPUs or devices, as it maintains order and efficiency. Data transfers can be synchronous or asynchronous. In synchronous transfers, data moves according to a clock signal, ensuring all components act in unison. Asynchronous transfers, on the other hand, do not rely on a shared clock and use handshaking signals to coordinate. Each method has its advantages, with synchronous transfers being faster and asynchronous transfers offering more flexibility. Direct memory access, or DMA, is a feature that allows certain hardware subsystems to access memory directly, bypassing the CPU. This speeds up data transfer for tasks like disk operations or multimedia streaming. DMA controllers manage these transfers, freeing the CPU for other tasks and improving overall system efficiency. The width of the data bus determines how much data can be transferred at once. A wider bus can carry more bits simultaneously, increasing the speed of data movement. For example, a 32-bit bus can transfer 4 times as much data per cycle as an 8-bit bus. Upgrading bus width is a common way to boost system performance. Address decoding is the process by which the system determines which memory location or device should respond to a given address on the bus. Decoders analyze the address signals and enable the appropriate memory chip or peripheral. This ensures that only the intended component reacts, preventing errors and conflicts. To ensure data integrity, computers use error detection techniques during data transfer. Parity bits, checksums, and error-correcting codes help identify and correct mistakes that may occur during transmission. These safeguards are essential for reliable computing, especially in high-speed or noisy environments. In summary, data transfer between registers, buses, and memory is the backbone of computer operation. Each component plays a unique role, and their coordination ensures efficient processing and storage of information. From the rapid exchanges within the CPU to the complex management of system-wide data flow, understanding these mechanisms is key to mastering computer architecture. Thanks for joining this deep dive into data transfer. Keep exploring to unlock even more secrets of computing.